So here we are, as I told you in the previous lecture, we will learn how to find out eigenvectors and eigenvalues numerically. So one of the most common method used for finding eigenvalues and eigenvectors is the power method. So we have the power method, which is the largest, we find using the power method the largest eigenvalue in magnitude. So the largest eigenvalue in magnitude. So we are not finding all the eigenvalues here, but the largest one. And also the power method does not work for repeated eigenvalues. So if the largest eigenvalue is repeated, then the power method will not work. So let me write that down. Does not work for repeated eigenvalues. Okay. Now to or the method of using the power method, the algorithm is as follows. So I'll just write it down here in normal words, where you have, let's assume a guess x0 for eigenvector Okay, before this, you all know that to find out the eigenvalues and eigenvectors, the formula or the equation that we solve is A times, I didn't write it before, so we have A times the eigenvector x is equal to the eigenvalue lambda times the eigenvector x. And the eigenvector x is a non-zero vector, so this vector here, x, the initial guess is we are guessing it as an eigenvector, and this should be a non-zero vector. And also we will choose one component of this vector to be unity, which means to be 1. So one of its elements of the vector x0 will be 1 all the time. And then the second step will be, we'll find another vector y1, which we'll get when we multiply the matrix A times x0, the initial guess. And once we're done with this, then we will scale out y1 by lambda times x1. So we can say we'll find y1 as the lambda times another vector, or the same vector, we'll scale it out, and we'll have the next, when we scale out the lambda, we'll have it here as x1. And this we'll do by keeping same component, or the same component that we chose here to be 1, the component to be unity, the same component to be unity. So we'll keep it as 1. And the fourth step would be to repeat steps 2 and 3. So we'll repeat step 2 and 3 until we have the eigenvalue converging. So until the eigenvalue or even the eigenvector, it's anyone, converges. So how will we know that the eigenvalue is converging is by finding out the absolute relative approximate error. So this one here, we will take the eigenvalue of the present step, let's call it I plus 1, minus the previous step, so eigenvalue I, divided by the eigenvalue at the present step times 100. And this here will be less than, so you do this until you have some pre-specified tolerance. So let's call it until this is less than equal to a pre-specified tolerance ES. So a tolerance will be given to you, let's say 5% or 0.5%, and until that tolerance you will keep doing steps 2 and 3 to get the largest eigenvalue and the eigenvector related to it. So this will get more clear now when we try to solve an example. So we'll use power method to find largest eigenvalue by magnitude. Why am I saying by magnitude is because the eigenvalue, we take the absolute value of it, not like it's not about the negative or positive, we take it by the magnitude, the largest eigenvalue by magnitude of and corresponding eigenvector. So the vector, so the matrix that's given to us is 1.5 here, minus 0.5, minus 0.5, 0, 0.5, 0, 1, minus 0.5, 0, and let's say that the initial guess of us x0 is, so x0 should be a non-zero vector, it will not be all zeros, and one of its elements should be 1. So I'm taking here an initial guess of vector where all are ones, but let's say that this is the element that will continue to keep 1 all the time. So this is our element for unity, let's say, and we'll keep it 1 always. And now I want to give you all a direction to do this easily. So rather than doing it step by step like how I showed you here, step 1, step 2, step 3, but in one line you can do it everything together. So let's say we'll have a times x0, the initial guess, we'll find it out, and that will give us y1, and we know we can scale out y1 to get lambda times x1, right? So let's start with the matrix times the initial guess x0. So our matrix I'll copy it from above. Okay, times x0. So x0 is 1, 1, 1. This will give us y1, which is 2.5 minus 0.5 and minus 0.5. So once we got y1, now we'll scale it out into lambda times, so we know that we have to keep, as we told above here, so we told that we'll keep this element here to be 1 always, the first element. So this element we want to keep it 1 always, so we'll divide this by 2.5, and so we will divide each of these elements here by 2.5. Therefore we'll scale out 2.5, something like taking out common as 2.5, and here we'll have 1, and then we'll have here minus 0.2 and minus 0.2. Okay, now for the next step we'll calculate a of x1 now. So we already copied a, so I can take it times x1 now. So we know that this is x1, which is 1 minus 0.2 minus 0.2. We'll get now y2 value. So this vector will be y2, which is 1.3 minus 0.5 minus 0.5. And now, can you all tell me what we will scale out? What will be the value of lambda? Yes, it's 1.3. So if we scale out 1.3 now, yes, Hiba and Honey, that's correct. And we'll get here now then 1, and here we have minus 0.3846 minus 0.3846. So we'll continue this step, but before that let me show you the absolute relative approximate error for these two eigenvalues that we just got here. So we have absolute relative approximate error is lambda of 2 minus lambda 1 divided by lambda 2 times 100, which is 1.3 minus 1.5 not 1.5, 2.5 divided by 1.3 times 100. Can you all give me the percentage for this? Yes, correct. So that's 92.31%. So as you can see that the error is very high, so we have to do more steps to get the correct eigenvalue. Now I'll not do all the steps, but just write down the values so you can see it at a glance here. So let's say we have a table. So here we have our I values and the lambda I here, and then we have the xi, which are the eigenvectors, so eigenvalues, eigenvectors, and the absolute relative approximate error. So for 0, or not 0, for 1, the lambda 1 we got was 2.5, and the eigenvector that we got was 1 minus 0.2 minus 0.2, and for that we cannot calculate the error. Then when we took I is equal to 2, we got the second lambda as 1.3 and the vector as 1 minus 0.38462 and minus 0.38462. And the error percentage we got is 92.307%. Now for if you calculate the third I, you will get the eigenvalue as 1.1154 and the eigenvector as 1 minus 0.44827 and same again 44827. And for the fourth, we have the eigenvalue as 1.0517 and the eigenvector is 1. So as you can see at the top, the 1 is always there because we kept that unity and we kept it same all the time. So we have here minus 0.47541 and minus 0.47541. And for this one, we got the error as 16.552. Here we got 6.0529. And now for the fifth I, we have the eigenvalue to be 1.02459 and the eigenvector is 1 minus 0.48800 minus 0.48800. and the error percentage is 1.2441. So let's say that we were given that ES, the tolerance, to be 0. Or let's say it's 2%. So this value here is less than 2%, so we can stop here in that case if the tolerance was given to you as 2%. Now the exact solution to this matrix is the eigenvalue exactly is 1, or let me write it, lambda is 1, and the eigenvector is 1 minus 0.5 and minus 0.5. So you could see here slowly we were converging towards the exact eigenvalue and the eigenvector. But it would take us some more steps to converge to the exact one. But in question, if I give you a tolerance, then you could stop at the tolerance. So that's it for the power method. Do you all have any questions related to power method? Please ask me now.
Miss,
Yes.
the initial guess will be given.
For you all, yes, I'll be giving you guesses.
Okay, thank you.
You're welcome. Any other questions? Any other doubts?
Miss, also you will give us the number of I, or just we have to calculate the relative error?
It will differ. I could say you number of iterations. I could say you do 5 iterations. I could say you do it until the tolerance is 2%. Then you have to calculate EA. It depends. I could change the question to any type.
Okay.
Okay. Okay. No doubts? No one else? Then we go to the next topic of ours, which is ordinary differential equations. So the next topic of us is ordinary differential equations. And the first question is, of course, what are, I'll just write it in short form, what are ordinary differential equations? So this is ordinary differential equation. So it is equations that involve derivatives of one or more functions. So let's say we have equations like dy by dx is equal to 6x plus 1, and we have equations like y derivative or y prime plus 3 by x times y is equal to x squared, or we can have d squared y divided by dx squared minus 2 times dy by dx minus 3y is equal to 0. Also, we could have equations like 4x squared y double prime plus 4x y prime plus y is equal to 0. So these are some examples I've given to you, and here this one is a first derivative or first order derivative. Okay, so as you can see over here that every equation has a derivative, right? So this one here is a derivative, this one here is a derivative, here we have derivatives, and here we have more derivatives. So these are differential equations. Now we can find out the order of these equations here. So this one here is of order 1 because it's d to the power 1 times y, and the order of this equation here would be the highest order. So let me not say you that part now. Maybe just we'll say this is first order equation and this is the higher order equation. Okay, now we can see we have different notations here also. Sometimes the differential the derivative is written as dy by dx, and sometimes it's written as y prime and y double prime. We'll discuss this in some time. And so here we can say that we begin with information that tells us how a system is changing, and we seek information about the function, or you can say about the original function or formula. Okay, that represents that change. So what we are saying is that when we have a function that looks like this one here, this equation tells us that the rate at which the value of y is changing depending on the value of t. So the value of y here is, the y is a dependent variable. You can say it is a dependent variable, and this one here is independent. And we are seeing how the y is changing depending on the value of t in differential equations. And now let's look at some of the notations that we'll come across. So derivative notations. So we have the Leibniz notations, which are dy by dx, d square y by dx squared, and dqy by dx cubed, d to the power 4 or d fourth y over dx to the power 4. So those are derivatives in the Leibniz notation, and then we have the Lagrange prime notation that also you will see in this course or in this lesson, which are as y prime, y double prime, y 3 prime, and y 4 prime. So from the fourth prime, it is represented as a number rather than dashes. And then there is also one more notation which is less common notation, the Newton's notations. So you have y dot, y double dot, y triple dot, and then similar to the Lagrange, here we'll write the number 4 above. So this is mostly seen in science or mechanics with respect to time, but we'll not be using this notation in our lesson here. And we also have two types of differential equations. So types of differential equations. So there are two types of differential equations, the ordinary differential equation and the partial differential equations. So ordinary differential equations are involves ordinary derivatives with respect to one independent variable so we include derivatives with respect to one independent variable. And in partial differential equations, which we'll not be doing in our course, it involves partial derivatives with respect to multiple variables. Okay, so we'll be using the ordinary differential equations in our course. And now one major way we classify differential equations is by the order of a differential equation. So we use the order of the differential equation to classify them. So let's write that down here. The order of if my handwriting looks to you that's not clear, you can let me know because I'm writing fast, so it may destroy a bit. But if you inform me that you do not understand, I'll try to slow down. So the order of a differential equation is the highest order of derivative present in the equation. So it is the highest order of the derivative present in the equation. So let's say we have a differential equation that looks like this here. Plus 2y is equal to sine x. And let me write down all my example differential equations. So we have minus 6y double derivative plus 9y or y prime is equal to 0. And then you have y double prime plus 4x y is equal to e to the power x, and here you have dy by dx squared is equal to 4x. Now let me number them: 1, 2, 3, and 4. So for the very first differential equation, what is the order? The order, as I just told you before some time, the order for the first equation, the differential, the derivative is this one here, dy by dx, and this is of first order because the degree is 1, you can say. Now for this one here, for the, or first let's say for the second equation that we have, differential equation, we have three orders here. This is order 1, order 2, and order 3, but we'll take, as we said, the highest order, right? We'll take the highest order, so that will be y3 prime, so this will be third order equation. So this is a third order equation. Now for our equation number 3, can you all tell me what is the order? Second order. Yes, that's correct. That's correct. So here we have second order. Can you all tell me for the fourth equation what is the order? No, that's wrong. That's wrong. So the order of the, yes, Lamia, that's correct. So the order of this equation here is for the derivative, not the power of the derivative, but the derivative. What is the order of the derivative? It is dy by dx, which is the first order. So this is somewhere that you might get confused. So this is not a second order, but a first order with power of 2. Okay. Now let's talk about the solution of a differential equation. So for a differential equation, of order n, a solution is a function that satisfies the equation on some interval I. And the function needs to have at least its first and derivatives continuous on this interval I. So in general, we don't want a point, you can say, that is a solution to a differential equation. We want some type of a curve or a function that satisfies the differential equation. And if we want, or if we are trying to solve an order of equation that is in order n, then we will need to have its first n derivatives continuous on that interval. So let's say for solving a third order equation, we need to make sure that the first three derivatives are continuous on that interval that we are trying to find out the solution of. So let's take an example here, maybe then it might be more clear. So let's say yes, okay, let's say show that the function y is equal to e to the power 5x is a solution to the differential equation y prime minus 5 times y is equal to 0. So here we are given the differential equation and we are asked whether this is a solution to this equation or not. So it's very simple to do that here. We know to how to do this already, I believe. So what we do is we just take the solution and we put it in the differential equation and we check if it is true or not. So for the differential equation we also need the y prime. So our y is e to the power 5x and y prime will be 5 times e to the power 5x using the chain rule. And now if you insert it into this differential equation, we have y prime, which is 5 times e to the power 5x minus, here we have 5 times y, which is e to the power 5x is equal to 0. So you can see that 5 e to the power 5x minus 5 times e to the power 5x, they're same. So subtracting them would give us 0 equal to 0, which is true statement. So it is a true statement, therefore this is a solution. Y to the power y is equal to e to the power 5x is a solution to this differential equation here, right? So when we are given differential equations, we are supposed to find out the function, the original function related to that equation. Now, when we are talking about finding a solution, it's possible that more than one solution exists depending on the information that's given to us. So let's say, for example, let's take a question. How many solutions exist for the equation dy by dx is equal to 2x? How many solutions does exist for this equation here? So to get the function, the value of y, we need to antiderivative. We need to find out the antiderivative of 2x. So y would be antiderivative of 2x dx. So y will be equal to the antiderivative of this using the power. We'll have 2 above, we have 1 here, so plus 1 divided by 1, and that is equal to, sorry, divided by 2 here, not 1, so that would be divided by 2, and we have, therefore this would cancel and we would have here x squared and some constant c here. Now c could be any arbitrary number. It could be a 0, a positive number, a negative number, and there are many functions that fit this equation that's here. There would be many functions that would fit this one, so we can have infinite solutions to this problem here. So If you look at it graphically, it would look something like this one here. So x squared is something like this, but because we have c arbitrary, so we could have many different solutions to this single equation here. So what we say is that this here is a general solution, and it describes a family of functions that all satisfy the differential equation that's given to us. Now, how do we find out a particular solution? Or let me do it here maybe. So, how do we find out a particular solution? So for that, we are going to get our differential equation in this form here, and we'll be given an initial condition. So let's say here we have y of 1 is equal to 4. So this one here is initial condition, and so we already know first what we're supposed to find out is the general solution. So we have already found out in the above step here. So we have our general solution is y is equal to x squared plus some constant c. Now we are given an initial condition, that is when x is equal to 1 and y is equal to 4. So this initial condition will insert it into our equation, and we'll get here for y we have the value 4 is equal to x is 1 squared plus c. So c will be equal to 3 in this case here. So I hope you know how to solve that. So 1 squared is 1, and if you take it on the other side, it's 4 minus 1, that's 3. So we take the c is equal to 3 and we insert it back into the general solution here. That will give us the function to this differential equation, which is y is equal to x squared plus 3. So this is the particular solution for the differential equation given to us. So let me write that down too. So this here is the particular solution. Okay. Now let's say okay, before I say something more on differential equations, I believe you all have the knowledge of whatever I had taught you until now, from your calculus class, or I don't know which other course, but you should have the knowledge of the basics of differential equation. But I'm just giving you again a recap so you understand when I go to the numerical differentiation, numerical approximations of differential equations. Do you all already know differential equations? Can you all tell me? In which course did you learn about it? Math 1. Okay, calculus and linear. Great. So I hope you all remember, but I'm just giving you a recap so you all can catch up faster to what we are going to do and you understand what's coming up ahead. So still, I'll just give you a bit more differential equation examples here now. So we are going to solve some directly integrable differential equations only. So let me write that here. Directly integrable differential equations. Okay, so when the derivative can be written as a function of the independent variable only, so when the derivative here can be written as a function of the independent variable only, that's when we can directly integrate the equation. So we'll just basically use integration or antiderivatives to find out the solution of a differential equation. When that's the case, so when the derivatives are written as a function of the independent variable. I have some examples to solve. And the first one is dy by dx is equal to 6x squared plus 4. So here we are not given an initial condition, therefore we'll only find out the general solution. So we have here y is equal to the antiderivative of 6x squared plus 4 dx. So the differential equation here is written as function of only the independent variable, that's x here. And if you're finding out the antiderivative, now we'll have here 6x the power 2, we'll add it with 1 and divide it here by the 2 plus 1 3 plus 4, so x is to the power 0 here, plus 1 divided by 1 and plus some constant c. So we'll have y is equal to 2x cubed plus 4x plus some constant c. So that's the general solution to this differential equation given. And then we'll take another example, which is x squared y1 is equal to minus 1. And we are given an initial condition x of 1 is equal to 3. So now we'll find out the particular solution here, but first we need to still find out the general solution. But as you can see that the derivative function here is not written as y prime is equal to function of x. So we have to make it here y prime is equal to some function of x. So here we have minus 1 divided by x squared. Okay, now we can go ahead and find out the general solution for this. So y will be antiderivative of 1 over minus 1 over x squared dx. You can write this in a more better form, that is, you can say that this is minus x to the power of minus 2 dx. And then if you find out the antiderivative of that, you will get minus x minus 2 plus 1 divided by 1 plus some constant c. So we have here, okay, here we have minus 1. So it will be x to the power minus 1 plus some constant c, which you can write it as 1 over x plus c. So that's our general solution. Now we are given an initial condition when x is equal to 3 and y is equal to 1 here. So when we insert that into the general solution, we'll get y is 1 over 3 plus c. Okay, I'm making a mistake here. Okay, this is supposed to be y here. So we have x is 1, y is 3. X is equal to 1, y is equal to 3, and we have 3 and 1 here. So c is equal to 2. And now putting back or substituting the value of the constant c into the general solution gives us the particular solution, which is y is equal to 1 over x plus c, which is 2. So that's our particular solution. So that's an introduction to the differential equation once again. And now we will go and find out how to use numerical approximation methods to find out the ordinary differential equations. So Euler's method is a numerical technique to solve ordinary differential equation, and this is especially useful if we cannot solve a first order equation by hand using methods that we know already, something like we just saw directly integrable. Then there are others like separable, linear, homogeneous, Bernoulli, exact way of solving the differential equations. So those are the methods to do it by hand. But if we are not able to do that way, then we use the numerical approximation methods. And the first numerical approximation method that we'll use is Euler's method. And okay, so we'll learn how is the Euler's method derived. So we'll first work on the derivation of this one here. Let me write it down. So Euler's method can solve differential equation that looks like this one here. So we have dy by dx is equal to the function x comma y. So the function could have the values x or y or both x and y. And we are given an initial condition y0 is equal to y of 0 is equal to y0. So don't get confused here. The x will not always be equal to 0 here. It could change, but just for the form in which the Euler's method would work is this form here. So this is just a general format of writing it. And so let's say that we get a differential equation of this form here. So we have dy by dx plus 0.4 y is equal to 3 times e to the power minus x, and with initial condition y of 0 is equal to 5. So this one here is not in the form that Euler's method you can solve in. So we have to make it to that form here. So we'll keep the dy by dx on this side here, and we'll take the plus 0.4 y to the other side. That will be 3 e to the power minus x minus 0.4 y. So now it is in the format that we want, that is dy by dx is equal to the function of x comma y. So that's the function here with the initial condition y0 is equal to 5. Okay. So in differential equations, you are trying to find out the dependent variable as a function of the independent variable. So here in dy by dx is equal to f of xy, you're supposed to find out the value of y, which is the dependent variable, as a function of the given value x, that is the independent variable. So somebody will choose the value of x and give to you, and you have to find out the value of y in differential equations. Now let's look at graphically. So we'll have here, so let's draw the graph of y, the function f here. But keep in mind that although I'm drawing the function here as a function of x, the only thing which I know about y is the initial condition here. So I know nothing more than the initial condition here, as what we are given is dy by dx is equal to f of x comma y, and y0 is equal, sorry, y at x is equal to 0 is equal to y0. So I know the function here, I know it at x0, y0, the initial condition. So all I know is this point here, which is x0 and y0. Now, Euler's method basically says that we would approximate its vertical position, its y value, using the slope of the tangent line. So we'll take our initial condition here and we'll draw a tangent line or slope to this initial condition here. Okay, so now we have, let's say this is x0 here, so let's say this value here is x1, and so this value here is x1, and we have approximated the y value here. So this is not the exact y value of the function, but the y1 is approximated. This one here is x1, y1. And then from here, this point, we'll draw another tangent. Which is something that looks like this here. And let's take another value now here, which is x2. So we are using approximations, like we are using here, this is an approximate value, the y1, and we are using the approximated value of y1 to get the value of y2, which is again an approximated value. So that's y2. This coordinate here is x2, y2. So as you can see in Euler's method, we're using approximated values to go ahead and find out the next approximated value. And what we have to do now is to see, or maybe I'll draw another function, or so we have to calculate here now the slope. Maybe we can use this function here itself because it's clear enough, I hope. So the first thing we could do is now to find out the slope between the 2 points that we have, that is x1 and x2 here. So to find out the slope, we need the rise by run. So if you're finding out the slope here now, it will be the rise, which is y I plus 1. So this here is, I'm mentioning it as y I plus 1 minus yi divided by, here we have xi plus 1 and xi plus 1 minus xi. So that's the slope that we need to find out. So you can see the thing that we know about the slope of the tangent line is x0 y, or sorry, I'm just confusing you here, I guess. So let me make it more clear. So here we can find out the tangent line here, or the slope of the tangent line here. So that would be this slope here. Also, we know that from the differential equation here, we know that the slope here is equal, so, or you can say it is equal to f of x given y. So the slope can be replaced by f of xi comma yi here. So we can say that f of xi yi is equal to yi plus 1 minus yi here divided by xi plus 1 minus xi. Okay, now if we rearrange this one here, so we know we have the values of this one here. We know the value, we know from which point we are going to which point. We have the values of that, we have the values of yi. All we don't know is this yi plus 1. So we'll rearrange this to make yi plus 1 the subject of the formula, and that will give us yi plus the function at xi comma yi times, we have xi plus 1 minus xi, but this here, this part is the step size actually here. So the step size, we can say that this part here can be said as h. So we can replace this here by h, and that would give us the formula, which will look like this one here. So we'll have yi plus 1 yi plus f of xi yi times h, and that is the Euler's method. So that's the Euler's method, where you can say that h is equal to xi plus 1 minus xi. Now, do you all have any doubts in this? I might have confused you all a bit here. I'm not sure. If you all don't have doubts, then we can go for the example. But if you all have doubts, you can ask me now.
Miss,
Yes?
how this explanation can be related to the last example?
I'm sorry, I didn't get you.
How we can relate this explanation to the last example.
To
Because
the
the last example you solved it as this method, but now you said um, the formula of method is this. I'm just confused. What the relationship between this and the last example?
last example, you mean like which one? This one here? No, sorry.
Yeah, this one.
This one
Yeah,
or this one here?
no, this one.
You mean this one here?
Yes, this one.
This is not actually an example, but just showing you that when you take Euler's method, the derivative function should look like this one here. It should look like this. So if you get a derivative function that does not look exactly like that, but something like you have the derivative plus, you have something here plus something here. So you have to take those things and put it on the other side. That's what I'm saying here. So just to make it in this form, to make it in the form that we can solve Euler's method in.
Okay, thank you.
You're welcome. Okay, now let's work with the examples then. So we are given um, a differential equation dy by dx plus 0.4y is equal to 3e to the power minus x, and y of 0 is 5. And we are supposed to find out the value of y at x is equal to 3. What would be the value of y? And let's say we are given h is equal to 3 here. So can you all tell me, is this in the right form to solve the Euler's method? The differential equation? No. Yeah. So we have to make it in the right form here now. So we'll write it as dy by dx is equal to 3e to the power minus x, and we'll take plus 4y to the other side, which will be minus 0.4y. And once we're done with this, we know that our function x comma y is this function here now, which is 3e to the power minus x minus 0.4y. And now if you recall what we just did, you have your Euler's method is y of y sub I plus 1 is equal to y sub I plus f of x0 y0 times h. So y0 and x0 is given to us already. So here let's write it down. We have x0 is equal to, this is x0 for us here, and this is our y0. So x0 is 0, y0 is 5, and we know that the h is 3. So y1 will be y0 plus f of x0 y0 times h, which is 3. Or let's complete the formula at first. So x times h. So y1 will be y0, which is 5, plus f of x0 y0, which is we'll put the values of x0 and y0 into our f of xy here, this function. So we have 3e to the power minus x0, that's 0, minus 0.4 times y, and y0 is 5 here, times h, that's 3. So y1 is equal to 8 if you calculate this one here. And now let's write it in a table form to get clear, did we get y of 3 or not. So we have here I, xi, and yi. So when I is equal to 0, xi, x0 was 0 and y0 was 5. When I is equal to 1, we have x0 is, sorry, x1 we have is, to calculate the x0 or x1 you will use this formula here. So you have x of I plus 1 will be, let's say, xi plus h. Okay, so now here we have xi is 0 plus h is 3 for us here in this question. So we have 3, and yi we got for y1 is 8. So we can see that we got for y of 3 the value, right? So here this is the value for y of 3. So we can say y of 3, y at x is equal to 3 is equal to 8 here. So that's our solution. If there's any doubt, you can stop me and let me know. Okay. And then now let's calculate the relative true error. So the exact value at x is equal to 3 for this function is 2.763. So the true value, that is the true value here. And the true error is true value minus the approximated value that we just got is 8 here. So it's a big difference. And that is equal to minus 5.237. And therefore the relative true error would be approximately 190%, which is very large. And this is because the h value, we took a very large h, that because of which within one step we got our final answer. Let's try with taking a different h value. So let's try the same example, but this time with h equal to 1.5 here. So we will start again. So we have our Euler's formula is yi plus 1 is equal to yi plus f of xi yi times h here. So let's draw the table side by side. It makes things more clear. So you have I is equal to, sorry, I here, xi and yi. So when I is equal to 0, we know that xi is given to us as 0 and yi or y0 is 5. So x0 and y0, we have the values already given to us. And this time we took h as 1.5. So for y1, we would have here y0 plus f of x0 y0 times h. So that y0 is 5 plus, in the function that we have here, this function, we'll put in the value of x0 and y0. So that is 3 times e to the power minus 0, that's x0, minus 0.4 times y, which is 5, times h, now that's 1.5. This gives us the value of 6.5. So we can write that down here. So when I is equal to 1, x1 is xi plus h. So xi is 0 plus h is 1.5. And y1 we just calculated, we got it as 6.5. Is everything clear until now for everyone? Please let me know. Okay. If anything is unclear, please let me know. Okay. So now we will find out for, as we can see, when we take h is equal to 1.5, we'll have two steps here. So we'll go to I is equal to 2 and xi is 1.5 plus the h, we'll get 1.5 plus h 1.5, that's 3. So then we reach y of 3. So all we are interested to calculate is y at the value of x is equal to 3, right? So that's what is here. So we'll calculate y2 now. And for that we'll have here y1 plus f of x1 comma y1 times h. So we have y1 is 6.5 plus, so into our function we'll now put the values of x1 and y1. So we have 3 times e to the power minus 1.5, that's x1, minus 0.4 times y1, which is 6.5, times h, which is 1.5. And if you solve this one here, you get 3.604 as the answer. So here we have 3.604. So you can say that y of 3 is equal to 3.604. So if you do not draw the table, you will not clearly understand, like, this is for which value of x, this is for which value of x. It shows you more clearly on the table it is for which value of x, because in every time you're using the formula, you're actually using the previous value of x, right? For y1 you're using x0, for y1 you're using x0, for y2 you're using x1. So to know that you have found out the value for the x2 for the y2, it's better to draw the table because that makes it clear for you. So here you can say that this one, okay, no, let me not confuse you more. So here now if we calculate the true error, we have the exact value is 763 minus 3.604, which is equal to minus 0.841. So we can see the true error has reduced a lot. And now if we find out the relative true error, we'll have here, it will be approximately 30.44%. Even the true error has reduced from 190% to just 30% now. So the h, the more you have, the lesser step size you can say, the more the value will be accurate here. Now it's 11:31. I would like you to take the quiz now for 10 minutes, and then we'll be back and we'll start solving Rangakata of second order method. But I'm not sure if that's going to be a good idea actually, because you might get more confused. Okay, in that case, let me not solve the Rangakata method for today because we don't have enough time for the quiz and the work that we have in hand. So yeah, we don't have enough time for this. So let's Maybe let's do some questions now here. Let's take an example. So you're given the differential equations for Euler to be in the form dy by dx is equal to f of xy x comma y, right? And you'll have some initial condition y of 0 is equal to y0. And I'll give you an example here. So dy by dx is or plus 2y is equal to 1.3 e to the power minus x, y0 is equal to 5. So now can you write this as a first order differential equation in the above form? One more thing I would like to add, I'm not sure if I already added or I could not say it before. So Euler's method we only use for first order differential equations. Okay, so we are mostly interested in only working for, I think I'll only work with you all in mostly first order differential equations, and I'll see if I have enough time to work with higher order differential equations or not. Now, can you write this in the first order differential equation form as I've given above, the same format, and give me your answers now. Okay, 1.3 e to the power x minus 2y. Yes, that's correct. That's correct. So we'll write this as dy by dx is equal to 1.3 e to the power minus x minus 2y. And we'll also write our initial condition. So we can say that f of x comma y is 1.3 e to the power minus x minus 2y. Okay, now let's solve a second example. Or okay, so here we have a second example. We have e to the power y dy by x plus x square y square is equal to 2 sine 3x, and the initial condition is y0 is equal to 5. Can you write it in the above form and give it to me now? Two sine 3x minus x square y square divided by e to the power y. That's correct answer, Ryan. Okay, so we have here dy by dx is equal to, so we'll take this term here on the other side, so it will be minus, so we have 2 sine 3x minus x square y square divided by this term here. It's multiplying when it goes, or maybe let's not write it at once. So we have here e to the power y. And now in the next step, we'll take this term here, it's multiplying, and it will go and divide on the other side. So we have 2 sine 3x minus x square y square divided by e to the power y with initial condition y0 is equal to 5. So this is our f of x comma y, the function. Okay, great. So now I'll on the quiz for you all at 11:40. It will be open until 11:50, and you will have probably 6 to 8 minutes to solve the quiz. Okay? And before that, before we leave, do you have any doubts for today's lecture?
Miss, just to make sure, the true value will be given.
If it's complicated to solve it as a, if it's not directly integrable, yes, I will give you the true value if I want you to find out the true error.
Okay. Thank you.
You're welcome. Okay, so you all don't have any other doubts. I believe if you have doubts, I'm still here with you all. You can come and talk to me. I'm there with you all until 12. And yep, the quiz is open now. It will open at 11:40 exactly, and you'll have 8 minutes to solve it.
Miss, there is more topics to be covered in the next sessions.
Yes, I will. I think only in one more lecture on next Sunday, I guess. We will be doing the round cutter methods and, if possible, higher order differential equations. And that's it. The last lecture will be a revision lecture. Hopefully, I'll try my best to do that way.
Thank you, Miss.
You're welcome.
Miss,
Yes?
the quiz says that no questions have been added yet.
Whoa. Thank you. I didn't know that. Okay, I guess it's added now. I'll just change your timings. I can give you some more time to solve the quiz.